Friday morning, that's when we'll do the optional exam return, 8:30 in this room, optional, right? If you show up, go over the exam solutions, you get a little bit of extra credit. If you can't make it, or if you just don't make it, you're welcome to stop by my office during office hours or anytime my door is open, typically most of the time on a Monday, Wednesday, or Friday. Or you can email me to set up a time to meet, and you can still come and get that extra credit by reviewing the exam solution and your graded work. So that's what's coming up. And then next week, Monday, I won't be able to be here. I have to go out of town. So I will be posting a recording for you instead. So we won't meet in person next Monday. I'll post on D2L that information as well, but just as a heads up. So also next Monday, homework 5 is due. So hope everybody has at least gotten a chance to get it started by now. It's definitely not one that you want to wait until the weekend before to start. So try and get at least a start on it this week. You can get your questions answered. Unfortunately, I won't be here on Monday. I will keep an eye on my email in case you have questions, but Mohammed will have his office hours on Monday, so you can certainly check in with him as well on that day if you need some last-minute help, okay? But definitely don't wait until the last minute to get visual analysis sorted out, however you want to do that, either Tate Lab or your own computer. And yeah, it's just the one problem, just the trust problem for homework 5. Homework 6, which I haven't yet posted, that will involve finite element analysis as it applies to beams. And so in homework 6, I anticipate there being 2 problems to solve by hand. One would be a single axis axial force system, one would be a beam system, and then you'll use visual analysis to model that beam, okay? All right, any questions? All right, so if you walked in and didn't get these handouts, I think, okay, yeah, so just one of each. So this is for the load designation stuff that we'll start on Friday.
Thank you.
Yeah, you're welcome. All right. So last time we derived the beam stiffness matrix equation, all right? We went through that whole process of applying mechanics to a cantilever beam with a free end with a positive force, positive moment applied, and then we switched sides, repeated that process, and ultimately ended up with this set of equations, right? So 4 forces and 4 displacements. And I said this right here is your starting point for any individual beam element. All right, so you don't have to go through that whole process anymore. And this equation can be applied to any set of boundary conditions, right, for a single element. Now we'll go through and we'll apply that to an example. So I'll show you how we have to incorporate all those rules that we talked about that apply to finite element analysis when we introduced that concept a couple weeks ago. And then after going through an example that applies it to just a single element, we will go into applying it to multiple elements for a beam, all right? So we'll be doing the matrix overlay for the beam equation similar to how we did the matrix overlay for a truss assembly, okay? All right, so applying this to beam problems. First, we have all the rules that we talked about before apply, and see if I can quickly find that to recap. So this was at the Introduction to FEA lecture. I remember this from a couple weeks ago. On the second page of that intro, there were 7 rules that we wrote out. So all of these rules, of course, apply to our beam problems. And with beams, I think I mentioned this before, we want to always number our nodes left to right. All right, so Just remember that for beams. At each node, we will know exactly two things. All right, so we will know either the transverse force or the transverse displacement, and we know either the moment or the rotation. And remember, when we talk about these forces and moments that we know in the beginning or don't know in the beginning of our finite element analysis, we're only concerned with external forces. All right, so internally, we can figure that out later once we have the finite element analysis results. But for the entire finite element analysis problem, from the setup through the solution, all the F's and the M's are associated with external forces and moments, not internal. All right, so now we will apply this to a simple example. We have a simply supported beam with a applied moment at the left end. So applying our first two rules, all right, we have, well, first we'll number the nodes since they aren't already numbered. So numbering them left to right, we have 1 and 2. And then before we even go into any analysis, right, on this beam, it's pretty easy to figure out the deflected shape. So I'm going to go ahead and just sketch that so we know what to expect. And again, I recommend this practice anytime you start a problem. See if you can visualize the deflected shape. You don't necessarily have to sketch it, but try to just imagine how that structure will respond. All right, so it looks something like that. And remember, our sign convention for finite element analysis is always positive counterclockwise and positive upward. So at node 1, what do we know? We know that the displacement will be 0, right? Because there's a pin support there. So that means we do not know the applied force. Or I should say the reaction, right, in this case. We don't know the external force associated with that displacement. We also know that the moment is equal to negative m naught. That means we do not know the associated rotation. At node 2, roller support, so we know V2 is equal to 0. That means we do not know the associated force. And what else do we know at node 2? We know either theta or m. Which one do we know? Right, we know m. What is m?
0.
Right. There is no applied moment, so m is equal to 0. And the other reason we know that is because there's no fixed support there making a moment reaction that we don't know, right? Or forcing the rotation to 0. So up above, I will highlight these and just note that for the forces, right, those will either be applied external forces or reactions. And if neither exist, it's equal to 0. I think we already spelled that out in the intro to FEA with one of the rules, but I think it's worth reiterating here. So let's see, applied external force or reaction. Right, so if there's no reaction there and no external force, then we know that value is 0. All right, so basic steps here. After applying those first two rules, then number the nodes, identify, or I guess these are just the general steps, right? So number the nodes, we already did that. Identify the knowns and unknowns, that's what we did right here, right? So these are the boundary conditions. And then we'll start with that beam stiffness equation, right? So what we left off with on the previous page. Apply the boundary conditions and then solve for the unknown displacements. We always solve for the unknown displacements before we solve for the reactions. Solving for the unknown displacements first and then solving for the unknown forces, that process requires partitioning the matrices. Once we have our results from that process, then we will use our equilibrium equations to verify the results, right? But remember, I emphasized this at the beginning of our finite element analysis discussion, that even in a simple case like this, where you can readily solve for the reaction forces on this beam, don't do it. Resist the temptation, right? It can be very, very tempting to do that first, to figure out what those forces are. But just treat them as unknowns. If it's a reaction, treat it as an unknown, even if you can tell what it is just by looking at it, right? At the end, use that information to verify your results. That's really important to remember. All right, so applying our matrix equation to this problem, right, we have to still apply the boundary conditions that we identified. So V1 we said is 0 and V2 is 0. So again, I'm going to label these columns according to what they're going to be multiplied by. And with the two displacements being equal to 0, we can eliminate our first and third column from this matrix. On the other side of the equation, we know M1 over L is negative M0 over L, and we know M2 over L is going to be 0. So everything else we don't know. We're going to start with the rows that have known forces. So that's always how you identify the first partition, the rows that have known forces, right? So that's going to be rows 2 and 4 in this case, and then that's going to pull our values from the columns that still remain. So we're going to have negative M0 over L and 0 equal to EI over L cubed times a 2 by 2, first column 4, 2, second column 2, 4. And then that gets multiplied by theta 1L and theta 2L. All right, so this is your F equals K times X equation. Now, the first partition, remember, has to be square, right? That's one of the rules, or maybe at least it's implied from one of the rules. Because in order to solve this, we have to be able to invert that stiffness matrix, right? In order to invert it, it has to be square. Just because it's square doesn't mean it's invertible, though, right? So remember what happens if it's square but not invertible. That represents what kind of condition? You're on the right track. So if it's square but not invertible, it will be they won't be all independent equations. But what does that mean? What does that translate to, like in the physical sense.
Unstable.
Yeah, it's unstable, exactly. Good. All right. So, yeah, so I'll just note that here, right? Rows 2 and 4. We identify them as rows with known forces. All right, so we need to find the inverse of that stiffness matrix. Just as a refresher, since it's a 2 by 2, we'll write it out. So that's going to be L cubed over EI. Don't forget that you also have to invert that part, right? And then we multiply that by 1 over the determinant, which is going to be 12 in this case. And then for the inverse of a 2 by 2, that adjoint portion, you switch the row, or you switch the diagonal terms and then change the sign of the off diagonals. So that's going to land us on 4, -2, -2, and 4. So that's going to be L cubed over EI. And then bringing that 12 inside, we'll have 1/3, -1/6, -1/6, and 1/3 as our inverse. Now that we have that inverse, we just pre-multiply both sides by it. So that'll be inverse of K times the generalized force matrix is equal to the inverse of K times X, which leaves us with just X on one side, since this gives us the identity matrix. So we'll have L cubed over EI times our 1/3, -1/6, -1/6, and 1/3 times our forces, which is -m0 over L and 0. Is equal to θ1L and θ2L. So that gives us L cubed times m0 over EI times -1/3 and +1/6 is the result there. So then this is what we would plug into the second partition. And let's see, I missed something. What did I miss? Well, that's here. Or are you saying that this should be θ1 and θ2 instead of times L? Yeah, basically. So what I missed was the L in the denominator over here will give us a L squared right here, right? But what we want to keep it in terms of θ1L and θ2L, right? So, because that's what we're going to have for our second partition. All right. So now the remaining rows are the second partition. We'll use that to solve for the unknown forces. So plugging that in or to this equation, we'll have 6 EI over L cubed times, and I'm just bringing the 6 out in front of these guys to simplify the matrix math, And then for our displacements, we have m naught L squared over EI times negative 1/3 and 1/6. So we get F1 and F2 equal to 6 m naught over L. Right, those EIs will cancel. Times negative 1/6 and positive 1/6 is what that works out to. All right, so we got F1 is equal to negative m naught over L, and F2 is equal to positive m naught over L. Interpreting this on a sketch of the beam then, showing all forces, including the applied ones, we'll have F1 being m naught over L in the negative direction, and F2 is m naught over L in the positive direction. We have the applied moment, m naught. And then our deflected shape, right, is shown here where we found theta 1. So theta 1 is going to be equal to m naught L over 3EI. And from our first partition, right, we got the result a negative direction for theta 1 and a positive direction for theta 2. So the negative direction in FEA is clockwise, and our positive direction is counterclockwise. So over here we have m naught L over 6EI counterclockwise. All right, so I've already interpreted that in the sketch of the deflected shape, but we also guessed that sketch in the beginning, so it is consistent with the results that we received. So that's a good sign, right? It also makes sense that the rotation at the left end, which is where the moment is applied, is twice the magnitude of the rotation on the right end, where there's no applied moment, right? So we'll just observe that theta 1 is equal to negative 2 theta 2, and that makes sense. Verifying with equilibrium now, right? You can eyeball sum of forces in Y. That's totally fine. So especially when it's obvious like this, all right? If it's a little more complicated, then I might want to see the whole equation written out. But for something like this, you could leave it at that and say, yeah, sum of forces in Y is 0. For summing moments about a point, though, I always want to see you write it out and show what point you summed the moments about and show that that equation does, in fact, come to 0. Questions? Okay. So that was demonstrating it with a pretty simple example, a single element. If you'd like to practice another single element application, there is a practice problem that is started on the next page here. So you can find the solution to that on D2L under the examples and practice problems folder. So now we will move on to, we'll move on to the matrix overlay. All right, so if we have multiple beam elements, and this is where problems will get a little more interesting, we are going to apply that same overlay approach that we did for trusses. It's just now we're using the 2 degree of freedom system equation that gives us more rows and columns per node, right? So here, I'm going to note this, right? We've already discussed that, but it's relevant here. Beams are 2 degree of freedom systems. right? And remember, you can tell the size of the overlaid matrix. How? It's based on two things. One we just talked about. How many degrees of freedom you have, and how many nodes you have, right? So, number of degrees of freedom times the number of nodes will give you the size of the matrix overlay. All right, and that corresponds to one row for each equation, right? Okay, so the next item on here that shows up says beams must be continuous, meaning no internal hinges. That's for this class, right? That just means in this class, I won't be providing you with a problem that has an internal hinge to deal with, because that gets a little bit more complicated. You have to manipulate the matrix a little bit more, add some degrees of freedom, things like that. So we're not going to mess with that in this class. All of our beams will be continuous for finite element applications. All right, so now, as long as both elements or all elements in your beam problem have the same E, I, and L properties, then it's really easy to just overlay the matrices. And in this class, they will always have the same E, I, and L properties, so you won't have to worry about normalizing that term for beams the way we had to think about that for trusses, okay? Because it gets more complicated with beams because you have the L cubed to think about. So then as long as that's the case, then this is going to be the size of your overlay, or this is going to be your overlaid matrix for a two-element system. So we can see the first element showing up in the first 4 rows and columns, and the second element showing up in the second 4 rows and columns, all right, the last 4, where there's the overlay, right, the overlap occurs at node 2. So I'm just going to label the nodes, or the rows and columns according to node, all right, so there's node 1, node 2, node 3, node 1, node 2, node 3. Now, the way I've written it out here, we still have all the L terms inside the matrix, but remember, we can just get rid of that by dividing all the moments by L. And so that eliminates, when we divide both sides, all right, that eliminates one L term in those rows. And then we still have some L's showing up in the columns that are associated with rotations, so we multiply those rotations by L, effectively bringing that out of our matrix and into that column vector. All right. Maybe that'll help a little bit with the heat. So, okay. Any questions so far? Yeah.
You said the overlay matrix is degree of freedom by number of nodes.
Mm-hmm.
But you said this is a 2-degree freedom with 3 nodes.
Yes.
How does that correlate to this?
So we have 6 rows and 6 columns.
So it's like 2 degrees of freedom for each
Right, yeah, so 2 degrees of freedom times 3 nodes. Yeah, so it's, 2 degrees of freedom per node, right? Because you have translation and rotation at node 1, translation and rotation at node 2, translation and rotation at node 3. Yep. Yeah, so usually when we say it's a 2 degree of freedom system, that we wouldn't say like this is a 6 degree of freedom system because there's 3 nodes, right? We would say it's a 2 degree of freedom system, and that tells you, okay, how many nodes are there? That's how large your matrix will be, right?
The entire matrix, right?
The overlaid matrix, yeah, will be 2 degrees of freedom per node, so 6 total columns and 6 total rows. Yeah, good question. Any others? Yeah.
Will the matrices always be symmetrical across the diagonal?
Yes, excellent observation. So you can see that, and I don't think I can easily draw the diagonal on this one just because of how I expanded it, but yeah, the matrices will always be symmetric on the diagonal, or with respect to the diagonal terms. So, knowing that, you can take advantage of that, and if you want, you can just write the diagonal terms and then one side of the matrix, fill that in, and then you can just say symmetric on the lower half or something. That's common notation. All right, so now we'll go on to an example, a couple examples actually, and these are already fully worked out, so we're going to talk through it, and I'm going to point out some key things to keep in mind throughout these solutions. So first of all, here we have 2-element beam, EI is constant, both have the same length L, so that checks all of those boxes. Again, in this class, that will always be the case for beam problems. But it's important to remember why and understand what that does for you. So we got a fixed support at node 1, roller support at node 2, and applied load at node 3 in the downward direction. Identifying the knowns and unknowns at each node, right? So that's written out here. Fixed support means we do not know, we do know that the displacement and rotation are 0, right? We do not know the reactions. Roller support at node 2, that means we know displacement will be 0, but we don't know the rotation, right? So that means we must know the associated moment. Since there is no applied moment, that's equal to 0. At node 3, it's a free end, so we don't know the displacements, but we do know both associated forces. And this is where a lot of folks say, wait, moment at 3 is 0, okay, I buy that, but I don't believe the moment at node 2 is equal to 0 because that beam is going to bend over that support. So there's going to be some moment inside that beam, right? You're absolutely correct about that. But remember, with this process, we are only identifying external moments and forces, right, in this step. So because there's no applied moment externally, we say M2 is equal to 0. All right. So then the next step shows the individual element matrix equations written for both elements. This step was important to do for truss problems, right? Because remember, with truss problems, we sometimes had different values for A, E, and L that we had to normalize before overlaying them. With beams, since I guarantee you in this class, every beam will have the same EIL factor, you can really kind of skip this step for beams, right? So you can go straight to the overlaid equation for beam problems and start there. So I'll note that, but I'm showing it in this example for 2 reasons. one, to show that, that's still where it comes from, but also I want to demonstrate, the details of that overlay. So we'll just note here, okay to skip this step for beams. Start here. All right, so element 1, 2, okay, we have, well, first I'm gonna jump down to our overlay, all right, and I'm gonna go ahead and I'm gonna label the columns, as I like to do. So the boundary conditions have already been applied here, and since the first 3 displacements we know are gonna be 0, right, all these columns are gonna be multiplied by 0, so we eliminate them from our analysis. The remaining 3 are associated with the unknown displacements. That's theta 2L, V3, and theta 3L. And notice the overlay, all right? So the overlay is going to come from the node 2 rows and columns in each of these individual element matrices. All right, so we have the 12 plus 12, negative 6 plus 6, negative 6 plus 6, and 4 plus 4 is 8. All right, so there's your overlay. I'm going to do it like this. Let's say that 2 by 2 and that 2 by 2 combine right there. All right, so now identifying the first partition, we look for the rows that have known forces. All right, so in this case, they are nicely lumped together. That won't always be the case. All right, sometimes you might have to pull them from different locations and piece them together, but here it happens to be that they are nicely lumped together. So we have our 3 rows there. So that's going to be, I don't like that highlighter color. I'm just going to use let's see. We'll go to purple. There we go. All right. So we got those 3 rows. So that's going to be these guys right here. All right, apply that. Take the inverse and solve for the unknown displacements. So notice that in this example and in the previous example, our results are going to be in terms of whatever applied force we know, right? So in this example, it's in terms of P, because we had an applied vertical load of P. In the previous example, we had an applied moment, M naught. All of our results were in terms of M naught, right? All right, so, and again, right, we have our rotations times L and displacements in the same vector. So remember, we did that to bring L's out of the K matrix, and that effectively creates a displacement vector that has this consistent units, all right, for each entry. So when we interpret our actual rotations, we have to bring that one of those L terms back out from this side and put it over here. So this will end up being a PL squared instead of a PL cubed for the rotations. But we want to keep this form for our second partition, right? So this is what we will then plug into our second partition to solve for the unknown forces. Those unknown forces are associated with the first 3 rows of this matrix. So that's going to be coming from this chunk up here, right? I will mark those in green. A little color coding there. Interpreting the results, all right, we have all of our forces in terms of the applied load P. That makes sense, right? The moment, right, remember we divided that by L, so when we actually apply it, it's going to be, we have to bring that L back over into this. So it's going to be PL over 2. We got a negative value for the moment. That means it's going to be counterclockwise, or excuse me, it's going to be clockwise, right? And then verifying equilibrium, all right? Sum of forces in Y checks out. And then summing moments, you can pick any point you want. Just demonstrate that sum of moments is equal to 0. Okay. Questions? Okay. All right, so a quick summary then. Now that we have gone through axial force systems and beams, I'll update this. All right, so the summary of axial force systems and now beams. So number of degrees of freedom, we have 1 for a single axis axial force system, 2 for multiple axes, or in global terms, right, if we're representing a truss. For beams, we also have 2 degrees of freedom. For beams, what do we know at each node?
The deflection or reaction.
Yeah, we know either V or F. What else? Theta or M, right? I know this feels repetitive and tedious, but I promise it's always a point of confusion at a decent level. So it's worth reiterating in class. All right, so the size of the individual element matrix K for beams, we had a 4 by 4. All right, so that's 2 degrees of freedom times 2 nodes for a single element. The size of the overlaid matrix for the whole system will be 2n by 2n, where n is the number of nodes. Okay, any questions? Yes.
So, if you have 2 fixed supports on a beam,
Mm-hmm.
then, and say a roller in the middle, then you would have 2 unknowns on one side and 4 on the other, right? How would that work?
So I can picture what you're saying. So you're talking about something like this, where you have, right? So this would be a 2-element setup, okay? So you would have a 6 by 6 overlaid matrix, but you would have known 0 displacements at nodes 1 and 3. The only degree of freedom that is not restrained, in other words, that is not 0, is going to be the rotation at this center node, right? So we can visually say, okay, so that also means that the only place where we can have a possible applied force would be the moment at node 2, right? So let's say we have an applied moment. Well, what will the deflected shape look like on this beam? Right, we have 0 displacement and 0 rotation at nodes 1 and 3. And we know we have 0 displacement at node 2, right? So we also know that if this moment is applied in the clockwise direction, right, it's going to kind of force this side of the beam down and this side of the beam up. So we can start there, all right, sketching that direction, and then bending to meet the support conditions. All right, so that's what your deflected shape you can expect to look like based on intuition, right? And I highly recommend you do that first and then solve the finite element analysis problem. Doing that will also help you to identify boundary conditions if you haven't quite sorted that out yet. So I don't know if this answered your question exactly, but were you speaking to what would the matrix look like? Okay, so we would still start with the 6 by 6, right? So we would still have this to start with. But once we identify all of the unknowns, we would have these 3 would all be 0, and then these 2 would also be 0, right? So that would mean our first partition would only be one value, right? So our first partition would just be a scalar equation, not even a matrix equation at that point. Really easy to solve, right? So remember when we talked about trusses and I said the more indeterminate the system is, the easier the FEA solution will be. That's because the more indeterminate your system is, the smaller your first partition will be. So the easier it will be to invert that, solve it by hand, right? And then use those results to find all of the unknown forces. Does that answer your question, or do you want to hear more?
I'm kind of wondering what the second partition would look like.
The second partition, all right, so the second partition would be all of the remaining rows, all right? So let's see, so this would be the one for the first partition. So your second partition would be what's above and below it, right? Or sorry, that's the wrong column. It would be this column, theta 2L, all right? So your first partition would be this 8, okay? And then your second partition would be a column vector, 6, 2, 0, negative 6, 2. And because all the other columns are just going to be multiplied by 0, right? So technically in the second partition, it doesn't have to be square. So you could, if you wanted to, you could include all 6 columns in your second partition. But that would just kind of be a waste of time to write it all out because 5 of those 6 columns are going to be multiplied by 0, right? So once you have a value for theta 2L, you just take whatever remained from your original matrix, right, after the first partition and use that.
Okay, that makes sense.
Yeah. Yeah, good question. Any others? Okay. Well, we are out of time, so I will see you on Friday. Hopefully some of you will show up at 8:30 and I won't be hanging out here by myself, so we'll see how that